On September 5th, 1977, NASA launched a spacecraft the size of a small car. It weighed 721 kilograms. It was powered by 3 plutonium-238 radioisotope thermoelectric generators, producing, at launch, about 470 watts of electricity, less than the power required to run a decent hairdryer. It carried 68 kilograms of scientific instruments. Its onboard computer had 69.63 kilobytes of memory. For comparison, a single uncompressed photograph taken on a modern smartphone is roughly 5,000 times larger. That spacecraft is now, as of today, the most distant human-made object in the history of civilization. It is somewhere beyond 23 billion kilometers from Earth. The signal it sends back, traveling at the speed of light, takes more than 22 hours to reach us. The ground stations that receive it must point their antennas with precision, measured in thousandths of a degree, to find it at all. And when the signal arrives, after its 22-hour journey across empty interstellar space, it carries a radio power of approximately 10 to the minus 17 watts, a femtowatt, a fraction so small it has no name in ordinary usage. Voyager 1 is still transmitting, and what it has found, what it found as it climbed away from the sun across the decades, through the outer solar system, past the giant planets, through the vast middle distance of the heliosphere, and finally across the boundary that no human instrument had ever crossed before, is the subject of this video. This is not a story about space travel in the conventional sense. Voyager 1 cannot stop. It has no brakes, no engine firing, no astronauts. It is a free-falling object moving under its own inertia through space, guided by gravity assists. It received decades ago and now destined to coast through the galaxy for billions of years. It is, in the most literal possible sense, a message in a bottle, thrown into an ocean so vast that the bottle will never be found and the message will never be read, except by us, as long as it keeps transmitting, which is the miracle of the whole thing. The story of what Voyager found at the edge of our solar system is a story about boundaries, about what happens when the sun's influence ends, about the physics of the space between stars, about how much of what we thought we knew about the solar system's outer structure was wrong until something went there and looked, and about what it means, philosophically, scientifically, humanly, to stand at the edge of something and stare into what is beyond. We are going to take that trip in order, starting from where Voyager began and ending where it is now. Chapter 1: The Grand Tour. Why Voyager exists at all. Voyager 1 almost did not happen. The mission exists because of a window. A planetary alignment so rare that it occurs only once every 176 years. The outer planets of the solar system, Jupiter, Saturn, Uranus, Neptune, arranged in a rough arc such that a spacecraft launched at precisely the right time could visit all. 4 of them using gravitational assists, using the gravity of each planet to accelerate towards the next without requiring additional propulsion. No rocket built in the 20th century or the 21st could carry enough fuel to reach Neptune under its own power on a reasonable timescale. The Grand Tour alignment made it possible to do it without the fuel, by borrowing momentum from the planets themselves. The window opened in the late 1970s. It would not open again until the 2015-20s. Gary Flandreau, An aerospace engineer at JPL identified this alignment in 1964 while working on a graduate project. He recognized that a spacecraft could ride the gravitational slingshots of the outer planets in sequence, arriving at each one with more velocity than it had before, reaching Neptune in about 12 years, rather than the 30-plus years a direct trajectory would require. The idea was elegant, almost improbable, a sequence of cosmic billiard shots, timed to the orbital mechanics of the solar system, executed with the computing resources of the 1970s. The gravity assist mechanism is worth understanding because it is one of the more unintuitive gifts of orbital mechanics. When a spacecraft approaches a planet, the planet's gravity accelerates it, bending its path. When the spacecraft leaves the planet, the gravity decelerates it by exactly the same amount. From the planet's reference frame, the spacecraft enters and exits with the same speed. The spacecraft appears to gain nothing, but from the reference frame of the Sun, the picture is different. The planet is moving, and the spacecraft is stealing a tiny fraction of the planet's orbital momentum during the encounter. The spacecraft gains velocity not in the planet's frame, but in the Sun's frame. The planet's orbital velocity is, in effect, transferred to the spacecraft. For something the size of Jupiter, the loss of momentum is completely negligible. A rounding error in the orbital mechanics of the solar system. For a 721 kilogram spacecraft, it is transformative. Each gravity assist added kilometers per second to Voyager's speed, compounding with each subsequent encounter. Without gravity assists, reaching Neptune in any reasonable time frame in the 1970s was simply not possible. With them, it was merely extraordinarily difficult. What Flandreau identified in 1964 was that this sequence of assists, Jupiter to Saturn to Uranus to Neptune, was geometrically possible in the late 1970s window in a way that would not recur for 176 years. It was not just a scientific opportunity. It was a one-time offer from the solar system itself, valid for a few years, expiring permanently. NASA's original plan was ambitious, a grand tour mission that would visit all 4 outer planets. But budget constraints trimmed the ambition. What became the Voyager program was a scaled-back version. 2 spacecraft, launched 16 days apart in 1977. Voyager 2 launched first on August 20th. Voyager 1 launched second on September 5th, but on a faster trajectory that would cause it to overtake Voyager 2 and reach Jupiter first. Voyager 2 took the full grand tour path, visiting all 4 outer planets. Voyager 1 took a faster route that would allow it to execute a close flyby of Saturn's moon Titan, judged to be scientifically valuable enough to sacrifice the trajectories to Uranus and Neptune. This decision had an unexpected consequence. Voyager 1's Titan flyby bent its trajectory in a way that sent it climbing steeply out of the plane of the solar system, on a course that would eventually carry it over the top of the heliosphere and out into interstellar space faster than Voyager 2. But before any of that, there were the planets. The Voyager encounters with Jupiter and Saturn were, by themselves, worth the mission's entire cost. Jupiter, when Voyager 1 flew past in March 1979, revealed itself to be a world of almost incomprehensible violence. The Great Red Spot, visible from Earth for over 300 years and known to be a storm, but its three-dimensional structure unknown, was resolved into a swirling, layered maelstrom hundreds of kilometers tall, with wind speeds exceeding 400 kilometers per hour at its periphery. The Jovian atmosphere showed banded jet streams, lightning-producing storm systems, and aurora visible in ultraviolet light. But the most astonishing discovery at Jupiter was not Jupiter. It was one of its moons. Io, the innermost of the 4 large Galilean moons, was photographed from close range for the first time, and what the cameras showed stopped mission scientists cold. Io was not the cratered, geologically dead world they expected. It was covered in volcanoes, active ones. As Voyager 1 was departing the Jovian system, navigation engineer Linda Morabito was examining the spacecraft's trajectory correction images and noticed something that was not supposed to be there: a bright crescent rising above the limb of Io, asymmetric and clearly not a moon. It was a volcanic plume, 280 kilometers tall, erupting into space. 9 active volcanoes would eventually be identified in the Voyager data. Io, the size of Earth's moon, was the most volcanically active body in the solar system, driven not by internal radioactive heating, as Earth is, but by tidal forces from Jupiter's immense gravity flexing the moon's interior as it orbited. The discovery of Io's volcanism was made from data sent back at a bit rate that modern USB drives can exceed by a factor of billions. And it was made by a person looking at a photograph. Saturn, reached in November 1980, brought its own revelations. The rings, visible from Earth as a flat disk with a few broad bands, resolved into thousands of individual ringlets, braided structures, spiral density waves, and gaps sculpted by the gravitational resonances of Saturn's moons. The F ring was found to be kinked and twisted around 2 shepherd moons, Prometheus and Pandora, whose gravitational influence kept the ring particles from dispersing. Saturn's moon Titan was photographed at close range for the first time, its surface hidden beneath an orange photochemical haze, denser than Earth's own atmosphere. A discovery that would, decades later, make Titan the target of the Cassini-Huygens mission. Saturn's moon, Mimas, revealed a crater so large, relative to the moon's size, that the impact that created it must have nearly shattered the entire body. All of this happened in the first 4 years of the mission. Then the planets were behind Voyager 1, and the long crossing began. Chapter 2: The Long Silence. Crossing the middle distance. After Saturn, Voyager 1's cameras were turned off, not permanently, but strategically. There was nothing to photograph that required their operation, and the power budget was finite. The scientific instruments that continued running were the ones designed to measure fields and particles, the magnetic field, the solar wind, the flux of energetic charged particles, because it was in these measurements, sustained continuously over decades, that the real science of the outer heliosphere would be found. The heliosphere is the bubble of space dominated by the sun's influence. Its outer boundary is where the solar wind, the continuous stream of charged particles flowing outward from the sun at roughly 400 kilometers per second, meets the interstellar medium and is slowed, deflected, and eventually stopped. The size and shape of the heliosphere was in the 1970s and 1980s almost entirely theoretical. No instrument had ever gone there. Models predicted that the solar wind would be gradually decelerated as it encountered the resistance of the interstellar medium, that there would be a shock wave, where supersonic solar wind became subsonic, and that there would be an outer boundary where the solar wind stopped entirely. But the distances involved were enormous, tens of billions of kilometers, and the predictions were based on indirect evidence and theoretical extrapolation. Voyager 1 became the instrument that would test these predictions. Not quickly. The spacecraft was moving at roughly 17 kilometers per second, which is extraordinarily fast by any human standard, and glacially slow by interstellar standards. The distance from the Sun to the predicted outer boundary of the heliosphere was roughly 100 to 120 astronomical units, 100 to 120 times the distance from Earth to the Sun. At 17 kilometers per second, covering that distance takes decades. During the crossing, the data kept coming. The solar wind data showed the expected pattern, a continuous flow of particles, gradually changing in character as Voyager moved further from the Sun. The flux of cosmic rays, high-energy particles from outside the solar system, accelerated by supernova shockwaves and other violent processes, increased steadily as Voyager climbed outward. This made sense. The solar wind acts as a partial shield against galactic cosmic rays, and the further from the Sun, the weaker that shielding. The increasing cosmic ray flux was one of the indicators that Voyager was approaching the boundary where the Sun's protective bubble ended. But there was something unexpected in the intermediate distance, in the region between the orbits of the outer planets and the heliospheric boundary, the interstellar neutral particles. As Voyager moved outward, its ultraviolet spectrometer detected a diffuse background of hydrogen and helium atoms, not part of the solar wind, but neutral particles drifting inward from interstellar space. These interstellar neutrals penetrate the heliosphere because they are electrically neutral and therefore not deflected by the Sun's magnetic field. They drift through the heliosphere slowly, interacting with the solar wind particles as they go, and their presence was detectable by the absorption they produced in the ultraviolet background. This was a first glimpse of the interstellar medium, the thin gas filling the space between the stars, from the inside. Not from a telescope, not from an inferred signal, but from a spacecraft physically inside the heliosphere, detecting the actual atoms of the interstellar medium as they drifted past. The significance of this cannot be overstated. Before Voyager, everything known about the local interstellar medium, its density, its composition, its temperature, was inferred from astronomical observations, the absorption of distant starlight by interstellar gas, the scattering of ultraviolet radiation, the detection of radio emission from interstellar hydrogen. These are powerful techniques, but they average over large volumes of space and cannot resolve fine structure. The interstellar neutrals detected by Voyager were the first in situ sample, particles that had actually come from the interstellar medium, captured and measured by an instrument that was physically present. The hydrogen and helium that Voyager was detecting had been drifting through interstellar space for millions of years before entering the heliosphere. The measurement of their density, temperature, and flow direction told scientists something about the local interstellar environment. the specific parcel of interstellar gas through which the solar system is currently moving, called the local interstellar cloud, a structure roughly 30 light-years across that the solar system entered somewhere between 44,000 and 150,000 years ago, and will exit in another 10,000 to 20,000 years. The solar system is not sitting still in the galaxy. It is moving through the galaxy at about 220 kilometers per second in its orbit around the galactic center. And as it moves, the heliosphere plows through the local interstellar medium like a boat through water, creating a bow shock-like structure at the leading edge and a long tail, the heliotail, at the trailing edge. Voyager 1, climbing out over the top of the solar system, is not heading into the undisturbed interstellar medium. It is heading into the side of the heliosphere, and then into the region where the heliosphere and the local interstellar medium interact. The interstellar neutrals it was detecting were the infiltrators, the particles that had crossed the boundary and entered the heliosphere's interior. The decades of field and particle measurements in the middle distance built a picture of a heliosphere that was more dynamic, more structured, and more complex than the 1970s models had predicted. The solar wind was not constant. It varied with the 11-year solar cycle, alternating between faster, more tenuous winds from solar minima and slower, denser winds from solar maxima. These variations propagated outward as waves in the solar wind, compressing and expanding the heliosphere on decadal timescales. The heliosphere, it emerged, breathes in and out with the solar cycle, expanding slightly during solar minimum and contracting during solar maximum. No one had predicted this when Voyager was designed. It emerged from the data over decades as the solar cycle repeated and the patterns became clear. Chapter 3: The Termination Shock. The solar wind's last stand. For roughly 30 years, Voyager 1 was crossing the region of the heliosphere where the solar wind blows outward at supersonic speeds. This is the vast majority of the heliosphere's volume, a region where the sun's particles and magnetic field dominate completely, and the interstellar medium is nowhere in evidence. The termination shock, predicted by heliospheric models, was the wall at the end of this region. The termination shock is where the solar wind transitions from supersonic to subsonic flow. The mechanism is the same as the sonic boom produced by a supersonic aircraft. When a supersonic flow encounters sufficient resistance, in the aircraft's case, the air ahead of it, in the solar wind's case, the accumulated pressure of the interstellar medium, the flow must slow down abruptly. It does so in a shock wave, a thin layer where the supersonic wind is suddenly decelerated, heated, and compressed. The solar wind's bulk kinetic energy, the energy of directed outward flow, is converted into thermal energy, random motion, magnetic turbulence. Theorists had predicted the termination shock would be somewhere between 75 and 100 astronomical units from the Sun. Voyager 1 was watching for it. The instrument that would detect the termination shock was the plasma science experiment. But by the time Voyager 1 approached the expected shock location, the plasma science experiment had failed. In 1980, after the Saturn flyby, the instrument stopped returning data. Its exact failure mode was never definitively determined. The plasma science experiment was the one designed to directly measure the solar wind's density, temperature and velocity, the very quantities that would show the abrupt change at the shock. This was a significant blow. Voyager 1 was approaching the most important boundary in heliospheric physics, and its primary instrument for detecting that boundary was dead. What remained was a set of complementary instruments that could detect the termination shock indirectly. The low-energy charged particle instrument, the cosmic ray subsystem, the magnetometer, and the plasma wave experiment could all provide evidence for the crossing, but none would give the clean, direct measurement of solar wind deceleration that the plasma science experiment would have provided. Throughout the 1990s and into the early 2000s, the Voyager team watched the data carefully for signs of the shock. The cosmic ray intensity continued to climb. The magnetic field began to show increased variability. And then, in 2002 and 2004, something happened. In 2002, the instruments showed a sudden surge in energetic particle intensity, a sharp increase in cosmic ray flux and energetic ion counts, lasting for a period before subsiding. The Voyager team interpreted this as a glancing encounter with the termination shock. The shock, which they now knew was not a fixed boundary, but a dynamic surface that moved inward and outward with the solar wind's variations, had briefly moved inward past Voyager 1 and then moved back outward. Voyager had been, temporarily, outside the termination shock, in the heliosheath, before the shock overtook it again. It was a preview, a taste of what was coming. Then, on December 16th, 2004, Voyager 1 crossed the termination shock for good. The event was detected not by any single dramatic measurement. There was no single instrument that could shout, "Shock crossed," but by the convergence of multiple instruments showing changes simultaneously. The magnetic field strength increased abruptly, nearly doubling. The cosmic ray intensity jumped sharply. The plasma wave data showed a change in the characteristic frequency of plasma, oscillations. And the low-energy particle data showed the directional flow of energetic particles change in character, becoming less ordered and more isotropic, as expected, for a region where the solar wind's organized outward flow had been disrupted. Voyager 1 had crossed the termination shock at approximately 94 astronomical units from the Sun. The prediction, 75 to 100 astronomical units, had been right. The boundary existed. The solar wind had spent its supersonic energy. Beyond the termination shock was the heliosheath. Think about what that confirmation meant in human terms. In 1977, when Voyager 1 launched, the scientists who built and designed the heliospheric instruments were operating on theoretical models that had never been tested against reality beyond the orbit of Saturn. The termination shock was a prediction, a careful, physically motivated prediction, but a prediction nonetheless. By the time Voyager 1 crossed it in December 2004, most of the scientists who had written those original predictions had been working on the Voyager mission for 27 years. Some of the original team members were retired. Some had died before seeing the crossing. The confirmation of the termination shock's existence at roughly the predicted distance was both a scientific triumph and a deeply personal one for everyone who had spent their careers watching Voyager inch outward across the solar system. Norman Ness, one of the principal investigators on the magnetometer experiment, described the crossing as the realization of something he had spent his entire career building toward. Ed Stone, who had been Voyager project scientist since 1972, noted that it was the first direct measurement of a structure that theorists had been modeling for 30 years. The numbers were right. The physics was right. What was striking about the crossing was how thin the termination shock was. The transition from supersonic to subsonic conditions appeared to occur over a distance of less than 1 AU, a fraction of the 94 astronomical units the solar wind had just crossed. The decades of supersonic travel, the vast interior of the heliosphere, and then, abruptly, within a single astronomical unit, the wall. The transition was sharp. The heliosheath, the region between the termination shock and the outer boundary of the heliosphere, was now Voyager 1's environment. Here, the solar wind still flowed outward, but slowly, turbulently, mixed with material reflected back from the outer boundary. Here, the interaction between the sun's domain and the interstellar medium was taking place. Here, the boundary of the solar system was within reach. Chapter 4, the heliosheath, the churned ocean at the edge. The heliosheath is not empty. That sentence needs unpacking, because the heliosheath occupies a region of space that is, by any ordinary measure, extraordinarily empty. The particle density is roughly 1 proton per cubic centimeter, approximately 10,000 times less dense than the air at the summit of Mount Everest, itself only about a third as dense as sea-level air. If you could collect all the matter in a cubic kilometer of heliosheath space, you would have a volume of material smaller than a dust speck. And yet, the heliosheath is scientifically the most complex region the Voyager spacecraft has passed through. It is where the sun's wind meets the interstellar medium and the physics of that meeting, the compression, the heating, the magnetic reconnection, the acceleration of charged particles, produces a turbulent, dynamic environment that the pre-Voyager models had badly underestimated in their complexity. As Voyager 1 moved through the heliosheath between 2004 and 2012, the field and particle instruments revealed a region dominated by what scientists call magnetic bubbles, structures in the solar magnetic field created by reconnection events, where field lines from opposite magnetic polarities merge and snap into closed loops. The heliosheath was filled with these bubbles, each roughly 1 astronomical unit in diameter, formed where the solar magnetic field had been compressed and rearranged by its encounter with the interstellar medium. The bubbles were unexpected. The pre-Voyager models of the heliosheath had predicted a relatively smooth, gradually decelerating flow of solar wind, nothing like the frothy, bubble-filled structure the data revealed. The magnetic bubbles are not cosmetically interesting and nothing more. They are functional objects in the heliosphere's energy economy. They are the mechanism by which the solar magnetic field is rearranged at the heliospheric boundary, taking the ordered radial magnetic field of the solar wind and reshaping it into a complex, tangled structure that can interact with the interstellar magnetic field. They accelerate particles, cosmic rays, and energetic solar wind particles get trapped and repeatedly scattered within the bubbles, gaining energy each time, producing the enhanced, cosmic ray fluxes that Voyager 1 was measuring. and they are the visible signature of magnetic reconnection, one of the most energetically important processes in plasma physics, operating at the boundary of the solar system. While Voyager 1 was traversing the heliosheath, its twin spacecraft was providing a crucial comparison. Voyager 2 had taken a slower trajectory and crossed the termination shock later in 2007 at approximately 84 astronomical units, 10 astronomical units closer to the Sun than Voyager 1's crossing location. This was immediately interesting. The termination shock was not at the same distance in all directions. The two spacecraft, crossing at different latitudes and different longitudes in the heliosphere, were sampling different parts of what was clearly an asymmetric boundary. The heliosphere was not a perfect sphere. The side facing the direction of the Sun's motion through the local interstellar medium, the nose of the heliosphere, was compressed by the ram pressure of the interstellar flow. The trailing side was stretched into the heliotail. The resulting shape was roughly that of a comet, with a blunter leading face and an elongated tail. Voyager 2 had something Voyager 1 lacked: a functioning plasma science experiment. Because the instrument that had failed on Voyager 1 was still working on Voyager 2, the 2007 crossing of the termination shock on Voyager 2 provided the direct, clean measurement of solar wind deceleration that the 2004 Voyager 1 crossing had lacked. The plasma data showed exactly what the models predicted. At the termination shock, the solar wind's bulk velocity dropped abruptly from about 400 kilometers per second to about 130 kilometers per second, and the plasma temperature shot up correspondingly as the kinetic energy was thermalized. The shock was confirmed precisely. One of the most unexpected findings in the heliosheath was the discovery of a stagnation region. In 2010 and 2011, Voyager 1's instruments showed something the models had not predicted. The outward radial flow of the heliosheath plasma appeared to slow toward zero, not just subsonic, but essentially stationary. The magnetic pressure in the heliosheath was building. The outward push of the solar wind was being matched and then overcome by the inward pressure of the interstellar medium, creating a region where the plasma was not flowing outward at all, just sitting, stagnating, waiting to be processed and ejected around the sides of the heliosphere. This stagnation region lasted for roughly 2 years in Voyager 1's data. The spacecraft was effectively immersed in compressed, heated, nearly stationary solar plasma in a zone where the Sun's wind had completely run out of forward momentum. The distance was somewhere around 110 to 120 astronomical units from the Sun. And then something extraordinary happened. In the summer of 2012, the measurements changed. The change was not gradual. It was abrupt, and it was total. In a matter of days, a geological eye blink in the time scale of the heliosphere, the environment around Voyager 1 transformed. The solar wind particles disappeared. Not the cosmic rays, those went up sharply, and not gradually. They went up in about 3 days, reaching new maximum values that held steadily. The magnetic field changed, its orientation shifted, though its strength remained roughly similar. And the plasma wave instruments detected, for the first time, a characteristic frequency of oscillation that corresponded not to the solar wind plasma, but to the denser, cooler plasma of the interstellar medium. Voyager 1 had crossed the heliopause. Chapter 5. The heliopause. Crossing the line. The heliopause is the outer boundary of the heliosphere. It is the surface where the solar wind, even slowed and heated and compressed in the heliosheath, is finally stopped by the pressure of the interstellar medium and can go no further. It is, by the most physically meaningful definition, the edge of the solar system. Inside the heliopause, the sun's particles dominate. Outside, the interstellar medium dominates. No instrument had ever crossed it before. No one knew with certainty what it would look like when it was crossed. The crossing in August 2012 was, in retrospect, exactly what a sharp, clean boundary should look like. The solar wind particle density dropped to essentially zero over a period of approximately 3 days. The galactic cosmic ray intensity jumped sharply, reaching a new plateau that reflected the largely unshielded flux of galactic cosmic rays in the interstellar medium. The magnetic field changed direction, aligning with the interstellar field rather than the solar field. The change was not gradual. Scientists had expected the heliopause to be a somewhat diffuse boundary, a broad transition zone where solar wind and interstellar medium gradually mixed over perhaps 10 or 20 astronomical units. What the data showed was a transition sharp enough that it was clearly delineated on timescales of days to weeks. The heliopause, at the location Voyager 1 crossed it, was a relatively thin and well-defined boundary. The distance? Approximately 121 astronomical units from the Sun, nearly 18 billion kilometers. The signal delay for that announcement was about 17 hours one way. There was, however, a controversy. When the data first showed the drop in solar wind particles in the summer of 2012, a spirited debate broke out within the Voyager science team and the broader heliophysics community about what had actually happened. Specifically, had Voyager 1 crossed the heliopause, or had it entered some previously unknown region within the heliosphere? A region that appeared to have interstellar-like plasma, but was still connected to the solar domain via the magnetic field? The controversy centered on the magnetic field orientation. The standard prediction was that at the heliopause, the magnetic field would change direction significantly. From the solar field, which spirals outward from the Sun in a pattern called the Parker spiral, to the interstellar field, which has a different orientation determined by the local galactic magnetic field. In August 2012, the magnetic field data showed an increase in field strength and a change in the character of the field's fluctuations, but not the large directional change that many scientists expected. This led some researchers, including Ed Stone, the Voyager project scientist, to initially hold back on declaring that Voyager 1 had entered interstellar space. Stone was careful. The plasma science experiment on Voyager 1 had failed in 1980, so there was no direct measurement of the plasma density and temperature to confirm that Voyager 1 was now in the denser, cooler interstellar medium rather than the rarefied hot heliosheath. The decisive evidence came from an unexpected source. In April 2013, Voyager 1's plasma wave instrument detected an oscillation in the local plasma, a wave driven by a burst of energetic particles from the Sun, generated by a solar storm in March 2012. That had finally reached Voyager 1 after traveling more than a year at nearly the speed of light. The frequency of the oscillation depends on the density of the plasma through which the wave propagates. The higher the density, the higher the frequency. When the wave hit Voyager 1 and caused the local plasma to ring, the frequency of the ringing told scientists the density of the plasma at Voyager 1's location. The density was 40 to 80 times higher than in the helios sheath. It matched the expected density of the local interstellar medium. Voyager 1 was unambiguously in interstellar space. The official announcement came in September 2013, based on the April 2013 plasma measurement. Voyager 1 had crossed the heliopause on or around August 25, 2012, at a distance of approximately 121 astronomical units from the Sun. It was the first human-made object to enter interstellar space. It had taken 35 years to get there. The months-long controversy over whether Voyager had actually crossed the heliopause is worth dwelling on because it illustrates something important about how careful science works and how careful it should work when the stakes are high and the result is unprecedented. The initial reports in the summer of 2012, before the April 2013 confirmation, attracted enormous media attention. Headlines declared that Voyager had left the solar system, then retracted when the scientific team expressed uncertainty. Some scientists said yes, some said not yet, and the public found the spectacle of physicists arguing about whether history had been made to be somewhat bewildering. But the caution was entirely appropriate. The heliopause crossing was, by definition, something no instrument had ever measured before. There was no prior template, no previous crossing to compare against. The team had predictions, but predictions are not data. The careful, evidence-based weighing of multiple instruments, outputs, including the critical plasma density measurement from the solar storm wave, was exactly the right approach. The announcement was delayed by 9 months because 9 months of additional data were needed to be certain. This is not a weakness of science. It is its strength. The same process that delays an announcement until the evidence is unambiguous is the process that makes the announcement, when it comes, reliable. The directional shift of the magnetic field, the missing piece of the puzzle, turned out to have occurred after all, just not in the way scientists expected. The field gradually rotated over the months following the crossing, eventually aligning with the interstellar field direction. The initial lack of a sharp rotation was a property of this specific crossing location and this specific configuration of the heliospheric boundary, not evidence that the crossing had not occurred. The heliopause was real. The solar system had an edge, and Voyager 1 had crossed it. Chapter 6: What interstellar space actually looks like. Here is what the interstellar medium at 121 astronomical units from the Sun looks like, based on what Voyager 1 found there. It is darker than anything you have experienced. Not dark in the sense of a moonless night sky, where the Milky Way is visible and stars cast faint shadows. Dark in the sense that the Sun, at 121 astronomical units, has an angular diameter of about 3 arcseconds, smaller than Jupiter appears from Earth. It is a bright star, certainly the brightest in the sky, but it is a star, not a sun. It would not warm you. The equilibrium temperature of an unheated surface at 121 astronomical units from the Sun is roughly minus 220 degrees Celsius. The particle density is thin but not zero. The interstellar medium at this location consists of roughly 0.06 to 0.1 protons per cubic centimeter, about 10 to 17 times less dense than the heliosheath plasma, and hundreds of thousands of times less dense than Earth's atmosphere. If you could sit still in the interstellar medium for a year, roughly 3 million interstellar particles would pass through your body. Not enough to notice, not enough to harm you, but enough to count. The magnetic field is weak, about 0.5 nanotesla, compared to Earth's magnetic field at the surface of roughly 50,000 nanotesla. But the interstellar field has a definite direction, pointing in a direction that is neither aligned with nor perpendicular to the plane of the solar system. The angle between the solar system's plane and the local interstellar magnetic field, a quantity of considerable theoretical importance for heliospheric models, has been estimated from the Voyager data as approximately 40 degrees, with significant uncertainty. This angle determines, in part, the shape of the heliosphere's boundary. A field that was parallel to the heliospheric boundary would produce a different pressure configuration than one at an angle to it. The cosmic ray flux at Voyager 1's location is higher than anywhere inside the heliosphere. But it is not isotropic. It does not arrive equally from all directions. There are subtle directional variations in the cosmic ray flux that reflect the structure of the local interstellar medium and the directions of the magnetic field lines along which the most energetic particles travel. These directional variations are providing some of the first direct measurements of the magnetic structure of the interstellar medium on scales of tens to hundreds of astronomical units, a scale that had been essentially unmeasurable before Voyager. There is also a population of particles in the interstellar medium that surprised the Voyager team: energetic electrons. Inside the heliosphere, the solar wind electrons have a characteristic energy spectrum determined by the solar corona's heating and acceleration mechanisms. In the heliosheath, the spectrum is modified by the shock and magnetic bubble interactions. But in the interstellar medium, Voyager 1 found a population of electrons with energies above 100 mega-electron volts, much higher than expected for the local interstellar medium at this distance from any obvious particle accelerator. The source of these electrons is not definitively known. One possibility is that they are cosmic rays accelerated in the Milky Way's magnetic structure and then transported along field lines to this location. Another is that they are remnants of energetic processes in the heliosphere that managed to cross the heliopause and survive in the near interstellar medium. The measurements are ongoing, and the electron energy spectrum is one of several pieces of data that the Voyager team is still actively interpreting. The plasma wave data has been perhaps the richest source of new information. Since crossing the heliopause, Voyager 1 has detected multiple episodes of electron plasma oscillations, waves driven by energetic electrons disturbing the local plasma. Each episode is triggered by a burst from the sun. A solar storm event releases a wave of energetic electrons that travels outward at speeds close to c, reaches Voyager 1 weeks to months later, and causes the local plasma to oscillate at the electron plasma frequency. By measuring this frequency in each episode, the Voyager team has been able to track how the plasma density of the interstellar medium changes with distance. and has found that the density is gradually increasing as Voyager moves deeper into the interstellar medium. This gradual increase is evidence that Voyager 1 is leaving the local interstellar cloud, the specific parcel of relatively low-density interstellar gas the solar system currently resides in, and approaching regions of denser interstellar medium beyond it. The boundary of the local interstellar cloud, based on the density gradient Voyager 1 is measuring, is somewhere in the region between 150 and 200 astronomical units from the Sun. Voyager 1 is currently at about 165 astronomical units. It may be approaching, or may have already entered, a denser interstellar region. If so, Voyager 1 is exploring a boundary that no prior measurement had been able to probe. Not the heliopause, where the solar wind ends, but the edge of the specific volume of interstellar space that the solar system has been drifting through for the past 100,000 years into whatever lies beyond it. Chapter 7. What the data revealed about the heliosphere's shape. Before Voyager crossed the heliopause, the heliosphere's shape was largely theoretical. Models predicted a roughly comet-like structure, blunt nose facing the direction of the solar system's motion through the interstellar medium, long tail trailing behind. The heliosphere was expected to be the product of the balance between the solar wind's outward pressure and the ram pressure of the interstellar medium flowing past it, with the sunward side compressed and the anti-sunward side extended. The Voyager data complicated this picture immediately. Voyager 1 crossed the termination shock at 94 astronomical units. Voyager 2 crossed at 84 astronomical units. The two spacecraft were at different latitudes and different longitudes in the heliosphere, and the 10 astronomical unit difference in their crossing distances confirmed that the heliosphere was not a sphere. The termination shock bulged closer to the Sun, on the side where Voyager 2 crossed the southern hemisphere of the heliosphere, suggesting that the southern heliosphere was more compressed. The interpretation involved both the interstellar medium's ram pressure and the asymmetry of the solar wind itself. The solar wind is not uniform. It is stronger and faster in the polar regions of the Sun, from the open magnetic field lines of the polar coronal holes, and weaker and slower near the solar equatorial belt. This asymmetry in the solar wind's output creates an asymmetry in the heliosphere's shape. Additionally, the Sun is moving relative to the interstellar medium at an angle, so the interstellar ram pressure does not strike the heliosphere head-on, but at an angle, further distorting the shape. After the heliopause crossing, the picture grew more complex still. The pre-Voyager models had predicted that the heliotail, the trailing end of the heliosphere, would be an elongated, roughly cylindrical structure stretching for hundreds of astronomical units behind the Sun. The tail was expected to be the softest, most distorted part of the heliosphere's boundary, where the solar wind eventually escaped laterally around the heliosphere's sides, rather than being stopped at the nose. Some models predicted the tail could extend for thousands of astronomical units. But in 2013 and 2014, data from an entirely different spacecraft, the IBEX mission, the Interstellar Boundary Explorer, produced a stunning result that overturned the comet model entirely. IBEX does not measure the heliosphere directly. It measures the heliosphere from the inside, from a position near Earth using a technique called energetic neutral atom imaging. When charged particles in the Helios heath exchange charge with neutral interstellar particles, they become neutral atoms that travel in straight lines, undeflected by magnetic fields, and can be detected by a spacecraft near Earth. By mapping the intensity and energy of these energetic neutral atoms as a function of direction, IBEX can build up an image of the heliosheath, a map of where the solar wind energy is being deposited as the solar wind interacts with the interstellar medium. The IBEX image showed a heliosphere that did not have a long comet-like tail. It showed a structure that was far more rounded, more symmetrical, more like a crescent or a croissant shape than a comet. The predicted elongated tail, hundreds of astronomical units long, was not visible in the IBEX data. Instead, the heliosphere appeared to have two roughly symmetric lobes extending behind the Sun, separated by a region of reduced neutral atom emission. The discrepancy between the comet model and the IBEX image generated immediate theoretical activity. Multiple papers proposing revised heliospheric models appeared in the months after the IBEX results were published. The current best understanding is that the heliosphere is a roughly croissant or crescent shape, with the lobes formed by the two magnetic flux tubes of opposite polarity that dominate the heliospheric magnetic field. The shape is determined not primarily by the ram pressure of the interstellar medium, as the comet model assumed, but by the magnetic pressure of the interstellar magnetic field threading the heliosphere's boundary. A strong interstellar magnetic field at an oblique angle to the solar system's motion will distort the heliosphere into a rounded crescent shape rather than an elongated comet shape. Whether this model is correct is still debated. The IBEX data are real. Their interpretation involves significant model dependence. And crucially, no spacecraft has yet visited the heliotail, the region directly behind the Sun, in the south direction away from the Sun's motion. Voyager 1 is above the plane and ahead of the Sun's motion. Voyager 2 is below the plane and also ahead. Neither is heading for the tail. What Voyager found is only part of the picture. The heliosphere is a three-dimensional dynamic structure, and the two Voyager spacecraft provide two narrow samples of it, 2 points in a structure spanning hundreds of astronomical units in all 3 dimensions. The full shape, the complete structure of the heliotail, the exact geometry of the heliopause in all directions. These remain partially unknown. But the Voyager data, combined with IBEX and the theoretical work they have inspired, has transformed our understanding of the heliosphere from a simple, approximately spherical bubble to a complex, magnetically shaped structure whose geometry reflects the detailed interplay of the solar wind, the interstellar medium, and the interstellar magnetic field. It is a structure more interesting, more textured, and more physically rich than anyone predicted when Voyager was designed. This is the pattern of discovery. The universe is never as simple as the models say it will be. It is always stranger and always more interesting, and the only way to find out what it actually is, rather than what the models say it should be, is to go there. Chapter 8: The Pale Blue Dot. When Voyager looked back on February 14, 1990, Valentine's Day, Voyager 1 turned its cameras off for the last time. Before it did, it took a photograph. Actually, It took 60 photographs, a mosaic of the solar system from the outside, a family portrait captured from a distance of approximately 6 billion kilometers, 40.5 astronomical units from the Sun. The images were assembled into a composite showing the Sun and 6 of the 9 planets then recognized in the solar system. Neptune was visible. Uranus was visible. Saturn, Jupiter, Earth, Venus. Mars and Mercury were too faint to appear at all. Earth occupies, in the most famous of these images, approximately 0.12 pixels, a fraction of a single dot of light caught in a scattered ray of sunlight that falls across the frame in a way that makes the planet appear to glow more brightly than it actually does. The effect of the sun scatter was unfortunate from a purely photometric standpoint. It makes Earth appear larger and brighter than the data strictly warrant, but it also gives the image its haunting quality. The planet looks suspended in something, cradled in a beam of light that has nothing to hold it, going nowhere, leading nowhere, marking nothing. Carl Sagan had pushed for the family portrait sequence for years before it was approved. The scientific value was modest. By 1990, the positions and basic properties of the planets were well known, and Voyager's instruments were far better suited to in situ particle and field measurements than to planetary photography from 40 astronomical units. The value Sagan saw was not scientific, it was philosophical. He wanted humanity to see its own planet from the outside, from genuinely outside, from a distance that placed the entire history of human civilization in its proper cosmological context. The engineer's objection was legitimate and deserves acknowledgement. Pointing the cameras near the Sun, even at 40 astronomical units, where the Sun is vastly fainter than it appears from Earth, risked permanent damage to the imaging optics through the solar glare. The cameras had been off for years. The imaging science system was no longer a priority. Turning it back on for a photograph that had no scientific return, and doing so in a configuration that risked damaging it, was not obviously the right call. The engineers who raised the objection were doing their jobs correctly. Sagan's counter-argument, made to NASA management and the Voyager science team over several years, was essentially this: the only thing wrong with taking this photograph is that the photograph has no scientific value. But no scientific value is not the only category of value. This moment, a spacecraft at 40 astronomical units, looking back at a solar system it was about to leave forever, would not come again. The specific geometry, the specific distance, the specific alignment of planets would never repeat in this configuration. If the photograph was not taken now, it would never be taken. And the photograph, whatever its scientific content, would be the first time in the history of the species that a human instrument had turned around from outside the solar system and photographed its home. The photograph was approved. The risk was accepted. The cameras were turned back on, the images taken, and the cameras were subsequently shut down permanently, as the engineers had recommended, immediately after. The imaging science system on Voyager 1 has not been used since February 14, 1990. The photograph was approved over the objections of engineers who worried about the risk of pointing the cameras near the Sun, the very risk that would eventually lead to the cameras being shut down permanently to prevent solar damage to the imaging optics. It was taken, It became almost immediately one of the most widely reproduced photographs in history. Sagan's reflection on the image, delivered at Cornell in 1994 and later published as part of his book of the same name, has been quoted so often that it risks losing its force through familiarity. But its argument is precise and worth engaging with directly. The argument is not sentimental. It is not saying that Earth looks small, and therefore we should be humble, in the vague way that photographs of Earth from the moon are sometimes used to argue for ecological concern or global solidarity. The argument is epistemological. Sagan was pointing out that the entire evidential basis on which human beings have constructed their history, their religions, their philosophies, their wars, their empires, every claim about what matters, who matters, what is worth killing for or dying for, was constructed on the basis of evidence gathered on that 0.12 pixel dot. And from this distance, from the outside, the dot looks like nothing at all. This is not nihilism. Sagan was not arguing that nothing matters because Earth is small. He was arguing that the smallness of Earth in the cosmic frame is a data point that should be factored into how we think about the conflicts and certainties that dominate human history. The certainties that drove the Crusades, the wars of religion, the colonial empires, the 20th century's ideological violence. All of them were generated on an object that, from 40 astronomical units, does not register as a distinct feature of the solar system. This is worth knowing. It does not answer the question of what matters, but it changes the frame in which you ask it. The pale blue dot image was taken, archived, and largely forgotten by the scientific community, which had more pressing data to analyze. Its cultural afterlife was Sagan's project, not NASA's. The full cameras were shut down after the portrait session, and Voyager 1 has never photographed anything since. It is not that kind of spacecraft anymore. It is a particle and field detector measuring the interstellar medium with instruments that will continue to function on declining power for another decade or so. But the image persists in ways that the data streams from the plasma wave instruments and the cosmic ray detectors never will. It is the moment when a machine built to measure things turned around and looked at us. Chapter 9. The Golden Record. What we sent and why attached to the side of each Voyager spacecraft, Voyager 1 and Voyager 2 both, is a 12-inch gold-plated copper disc. It is enclosed in an aluminium cover. On the cover are engraved instructions for playing the record, diagrams showing the correct rotation speed, a stylus to use, how to decode the video images encoded in the audio signal. There is also a pulsar map, a diagram showing the relative positions of 14 pulsars as seen from the Sun, with their frequencies encoded, allowing any finder who can locate the pulsars to triangulate the Sun's position in the galaxy. The record was assembled under the supervision of Carl Sagan and a small team over a period of several months in 1977, under significant time pressure. The launch window was not negotiable. What is on it? Greetings in 55 human languages, ranging from Akkadian, an ancient Semitic language of Mesopotamia no longer spoken by any living person, to Zulu, United Nations Secretary-General Kurt Waldheim's greeting in English. A message from President Jimmy Carter. Sounds of earth, rain, thunder, surf, wind, birdsong, a chimpanzee, a tractor, a mother's first words to her newborn child, a kiss, laughter, a train, a bus, a rocket launch, a pulsar, the human heartbeat, mud pots, a fire. Music, Bach's Brandenburg Concerto. Number 2 in F major and the Well-Tempered Clavier. Beethoven's Fifth Symphony and the String. Quartet number 13. Mozart's Magic Flute. Stravinsky's Rite of Spring. Louis Armstrong and his Hot Seven playing Melancholy Blues. Blind Willie Johnson playing Dark Was the Night, Cold Was the Ground, a wordless, haunting slide guitar piece recorded in 1927. A Peruvian wedding song, Javanese gamelan, Azerbaijani folk music, a Pygmy girl's initiation song, Georgian choral music, Bulgarian folk music, a Japanese shakuhachi piece, a Navajo night chant, 115 images encoded in the audio signal, diagrams of the solar system, mathematical and physical constants, the structure of DNA, human anatomy, a pregnant woman, a family, humans eating, drinking, and working, the Great Wall of China, the Sydney Opera House, an airport, a supermarket, a house in Kew Gardens, the Taj Mahal. The golden record is simultaneously a profound and a somewhat absurd object. It is a message addressed to no one in particular, containing no address, with no guarantee of delivery, and no expectation of reply. The probability that any intelligence will ever find either Voyager spacecraft is, by any reasonable calculation, extremely close to zero. In 40,000 years, Voyager 1 will make its closest approach to another star. A C+79 3888, currently in the constellation Camelopardalis, passing within about 1.6 light-years of it. This is not close enough for any planetary system in that vicinity to capture the spacecraft, and there is no known planet in the right position to intercept it. Voyager 1 will simply coast past at a respectful distance and continue into the void. In 1 billion years, assuming nothing has intercepted or destroyed it, Voyager 1 will still be in the Milky Way, somewhere in the galaxy's disk, orbiting the galactic center on a path determined by the combined gravity of billions of stars. The galaxy will be partway through its collision with Andromeda. The sun will have expanded into a red giant and destroyed the inner planets, including Earth. Whether any intelligence capable of finding and decoding the record will exist, either from Earth's lineage or from elsewhere, is entirely unknown. And yet the record was made. The argument for making it, Sagan's argument, was not that it would be found. It was that the making of it was itself valuable. That deciding what to put on a record addressed to the universe, what to include as a representation of human existence and human culture, what to say to an unknown intelligence across an unknown distance, was an exercise in self-understanding. The process of selection forced the question, what are we? Not politically, not nationally, not religiously, but fundamentally, as a species, as an inhabitant of this particular planet. What music do we make? What sounds define our world? What do we look like when we are being honest rather than impressive? The choices made are revealing. The absence of war or conflict on the record is deliberate. There is no military music, no monument to a battlefield, no speech by a conqueror. There is music from cultures that have dominated no empires and built no monuments that made it into other records. There's Blind Willie Johnson, a Black American street musician who was blind from childhood, died in poverty, and was buried in an unmarked grave. His music is on a spacecraft now beyond the solar system. there is a specific moment in the Golden Record story that does not receive enough attention. When Sagan's team was deciding what music to include, they consulted ethnomusicologist Alan Lomax, who had spent decades recording folk and traditional music from cultures around the world. Lomax argued that the selection should prioritize music that was genuinely representative of the full breadth of human musical culture. Not just the Western classical tradition that would have been the default selection if the decision had been made without deliberate effort to broaden it. The result is a track list that, in 1977, would have been considered unusual for any official representative collection of human achievement. Blind Willie Johnson, a blind black street musician from Texas, recorded in 1927 in poverty, dead by 1945. The Peruvian wedding song, the Azerbaijani folk music, the Pygmy Girls' initiation song. These are not the musical artifacts of empires or institutions. They are the music of people who were, by most of the world's usual measures of significance, insignificant. And they are on a spacecraft in interstellar space. The contrast with the usual vocabulary of human achievement, the great monuments, the famous rulers, the winners of history's competitions, is deliberate and worth sitting with. The Golden Record's implicit argument in its selection of content is that the music of a Pygmy girl's initiation ritual and the music of Bach's Brandenburg Concerto are equally valid representatives of what humans do with sound and time. That the voice greeting the universe in Akkadian, a language dead for 2,000 years with no living speaker, is as worthy of inclusion as the voice of the Secretary General of the United Nations. That what we make when we are not competing, not accumulating, not fighting, what we make when we are simply being human in our most human moments, is the truest representation of what we are. What is perhaps most striking about the Golden Record, from the perspective of 2025, is not what it contains, but what it was attempting to do. It was attempting to represent the whole of human culture, its sounds, its languages, its music, its faces, its places, in a form that could be decoded by intelligence of unknown character, using physical principles assumed to be universal. It was built on the assumption that mathematics and physics are universal languages, that a species that understands hydrogen's spin-flip transition frequency will be able to decode the pulsar map, and that a species that can decode the pulsar map will be able to follow the instructions on the cover and play the record. These are large assumptions. Whether they are correct cannot be tested, because no reply is possible or expected. The Golden Record is not a scientific instrument. It is a human gesture, an acknowledgement that Voyager was leaving the solar system, crossing into a space that is not ours, and that carrying something of ourselves into that space was the right thing to do. Whether it was the right thing to do remains, in a philosophical sense, debatable. SETI researchers and philosophers of science have argued for decades about whether actively broadcasting our existence and location to the universe is wise, given the unknown character of any intelligence that might receive it. The Golden Record is a passive version of this problem. It is not broadcasting continuously, but any intelligence that finds it would know where it came from. The debate in 1977 was not as fully developed as it is now. Sagan made the call. The record was made. It is out there. Now, beyond the heliopause, carrying a kiss and a heartbeat and blind Willie Johnson into the space between the stars. Chapter 10. The Power Problem. How long does Voyager have? Voyager 1 is running out of power, not quickly and not unexpectedly. The spacecraft's 3 radioisotope thermoelectric generators, the RTGs containing plutonium-238, produce electricity by exploiting the temperature difference between the decaying plutonium and the cold of space. Plutonium-238 decays with a half-life of 87.7 years. As the fuel decays, it produces less heat and therefore less electricity. At launch, the RTGs produced about 470 watts. By 2025, they produce roughly 240 watts, just over half of the original output, as expected from the radioactive decay law over 48 years. The available power has been declining by roughly 4 watts per year. This is not a crisis. It is a known, predictable, managed decline. The Voyager engineering team has been planning around it for decades. Shutting down instruments and heaters as power becomes too limited to run them, prioritizing the science instruments that are producing the most valuable data from Voyager's current position. The instruments that have been powered down or had their power reduced include most of the imaging science system, shut down after the 1990 family portrait session, the cosmic ray subsystem's high-rate mode, heaters for several peripheral systems, and most recently, in an engineering decision that made headlines in 2024, one of the 5 science instruments still operating on Voyager 1. In 2024, the Voyager team faced and solved one of the most unusual engineering challenges in the history of deep space operations. Beginning in late 2023, Voyager 1 started returning garbled data. Not no data, and not clearly corrupted data, but data that was internally inconsistent in a way that suggested a problem in the onboard computer rather than the transmission path. The spacecraft was still receiving commands correctly and responding to them. The science instruments appeared to be functioning, but the data they were generating by the time it was packaged for transmission home was unintelligible. The investigation took months, partly because of the 22-hour communication delay. Every command sent to Voyager 1 takes 22 hours to arrive. Every response takes 22 hours to return. A single diagnostic exchange takes nearly 2 days. A series of diagnostic tests, iterating on each result, takes weeks. The team worked through the problem systematically, sending commands, waiting 44 hours for the round trip, analyzing the result, adjusting the approach, repeating. The eventual diagnosis, a single chip in the flight data system, the component responsible for packaging data from the science instruments for transmission, had developed a fault. A small section of its memory was corrupted, causing it to generate garbled output whenever the data routing passed through that section. The chip itself could not be repaired. There was no way to replace it. There was no backup. It was a 47-year-old piece of hardware, 24 billion kilometers away, and it had a broken bit of memory. The solution was elegant. The engineers divided the corrupted chip's affected code across other sections of Voyager's available memory. Spread across different parts of the flight data system in a way that avoided the bad chip, stitched together by new pointers and routing instructions. The entire repair had to be designed, tested on Earth as best as possible, and then uploaded to the spacecraft without a live test in the actual hardware environment. One bad line of code, uploaded from 24 billion kilometers away, would leave the spacecraft permanently unable to communicate. The engineers uploaded it anyway. It worked. After recovering from this anomaly, the Voyager team announced that one of the remaining active science instruments would be powered down to preserve power for the others. The instrument selected was the plasma wave subsystem's electric field antenna, one component of the system that had been detecting the electron plasma oscillations in the interstellar medium. The decision was made after careful analysis of which remaining instruments were producing data that was irreplaceable. The instruments that survived the cut were the magnetometer, measuring the interstellar magnetic field; the low-energy charged particle instrument, measuring the flux and energy spectrum of interstellar cosmic rays and solar particles; the cosmic ray subsystem, measuring high-energy galactic cosmic rays; and the plasma wave subsystem's magnetic search coil antennas, which continue to detect plasma oscillations driven by solar storm events. These 4 instruments, running on roughly 200 watts of total spacecraft power, are the current scientific heartbeat of Voyager 1. Each is transmitting data that no other instrument in human history has been able to collect. There is nothing else at 165 astronomical units from the Sun. There is nothing else in interstellar space. Whatever these 4 instruments measure, it is the only direct measurement of its kind. The expected date of the last science data return from Voyager 1 is approximately 2030 to 2035, depending on how the power decline progresses and which instruments the team decides to sacrifice as the available watts continue to shrink. After that, the spacecraft will likely still be able to maintain attitude control and communications for some additional years. The transmitter and basic flight systems draw less power than the science instruments. Before the power drops below the threshold required to maintain any active systems. When the last signal stops, when the 22-hour radio silence from Voyager, one extends to 23 hours, to a day, to permanent, there will be no explosion, no crash, no visible event. The spacecraft will continue moving at 17 kilometers per second, approximately 3.6 astronomical units per year in perpetuity. In 10,000 years, it will be about 4 light years from the Sun. In 1,000,000 years, perhaps 70 light years. It will outlast the people who built it by an unimaginable margin. It will outlast any recognizable form of human civilization. In the time frame over which it will continue to exist, the Sun will have evolved significantly. The Milky Way and Andromeda will be in the early stages of their merger. And whatever species might find it will encounter an artifact so old that the time elapsed since its construction will be a significant fraction of the age of the universe. In 2031, if the current timeline holds, the last data will return from Voyager 1. A spacecraft launched in 1977, powered by a radioactive battery the size of a watermelon, will have transmitted continuously for 54 years, from a distance of more than 200 astronomical units, yielding scientific data that has required revision of the standard model of the heliosphere, the discovery of the Io volcanism, the first in situ measurements of the interstellar medium, the first crossing of the heliopause, and the first direct characterization of the local interstellar magnetic field. 54 years. 54 years of science from 69 kilobytes of onboard memory and a hairdryer's worth of power. Chapter 11: The Oort Cloud. The solar system, that nobody has seen here, is a fact about Voyager, one that is easy to overlook when you are focused on the heliopause crossing. Voyager 1 has left the heliosphere. It has not left the solar system. The heliosphere, the bubble of solar wind and solar magnetic field that we spent the previous chapters following Voyager through, is the sun's dynamic domain, the region actively shaped by the sun's ongoing output. But the solar system is larger than the heliosphere by a factor that is difficult to hold in your head. The solar system, in the most complete gravitational sense, extends to the Oort cloud, a vast spherical shell of icy objects believed to orbit the sun at distances, ranging from roughly 2,000 astronomical units to as far as 100,000 astronomical units. The outer edge of the Oort cloud is sometimes cited as the true edge of the solar system, because beyond it, the sun's gravitational influence becomes too weak to hold objects in stable orbits. Objects beyond the Oort cloud are not gravitationally bound to the sun and do not return. Voyager 1, at approximately 165 astronomical units, is not yet in the inner Oort cloud. The inner Oort cloud is thought to begin at roughly 2,000 to 5,000 astronomical units. At Voyager 1's current speed of about 3.6 astronomical units per year, the spacecraft will not reach even the inner edge of the Oort cloud for another 500 to 1,000 years, long after it has fallen silent. It will pass through the inner Oort cloud without transmitting, without being observed, without any awareness on our part of what it encounters. The outer Oort cloud, at tens of thousands of astronomical units, will take tens of thousands of years to traverse. Voyager 1 will be in the Oort cloud, entirely within the gravitational domain of the sun, for something like 30,000 years. The Oort cloud has never been directly observed, not because it is too small. Its constituent objects range from kilometers to tens of kilometers across, small but not microscopic, but because it is too far away. The reflected light from a 10-kilometer icy body at 50,000 astronomical units is far too faint for any existing telescope to detect. The Oort cloud's existence is inferred entirely from indirect evidence. The long-period comets that occasionally fall into the inner solar system, when a comet like Halley's or Hale-Bopp, or more recently Comet Leonard, or the extraordinary C/2014 UN-271, Bernardinelli Bernstein, a comet with a nucleus estimated at 137 kilometers across, the largest Oort cloud object ever detected, falls into the inner solar system. It comes from an orbit with a period of millions of years and an aphelion extending thousands to tens of thousands of astronomical units from the sun. These are Oort cloud objects that have been perturbed from their stable orbits by the gravitational influence of passing stars, by the tidal force of the galactic disk, by encounters with molecular clouds, and fallen sunward along trajectories that bring them through the inner solar system for the first time. The orbital statistics of long-period comets allow the Oort cloud's structure to be inferred, its inner and outer boundaries, its population, its total mass. Current estimates suggest the Oort cloud contains between 1 trillion and several trillion icy objects, with a total mass of roughly 1 to 38 times Earth's mass. distributed in a roughly spherical shell extending from the inner boundary at 2,000 to 5,000 astronomical units out to the outer boundary at perhaps 100,000 to 200,000 astronomical units. The composition of Oort cloud objects is thought to be primordial, icy bodies made of water ice, carbon monoxide, carbon dioxide, methane, and other volatile compounds that condensed in the early solar system and were then scattered to their current orbits by gravitational interactions with the giant planets during the period of planetary migration 4 billion years ago. They are, in a sense, the original building material of the outer solar system, preserved in the deep freeze of the Oort cloud for 4.5 billion years, rarely disturbed, occasionally falling inward as comets when a galactic perturbation nudges their orbits. The Oort cloud is therefore a time capsule. The icy bodies currently drifting at 50,000 astronomical units formed in the same disk of gas and dust that formed Earth, Jupiter, the Sun, formed from the same molecular cloud that collapsed 4.57 billion years ago, condensed the same volatile compounds that were present in that cloud, and then were flung outward in the chaos of the early solar system's dynamical evolution. When a long-period comet falls into the inner solar system, when something like Comet Hale-Bopp makes its spectacular appearance and then recedes for a return in 2,500 years, we are watching a piece of the original solar system making its first or near first approach to the Sun since it was scattered outward in the solar system's infancy. The chemistry of long-period comets, measured by spectroscopy as they warm in the Sun's vicinity and release their volatile compounds as a coma, is therefore a direct probe of the chemistry of the early solar system's outer regions. The water in comets has a specific ratio of deuterium to hydrogen, the DH ratio, that encodes information about the temperature at which the water ice condensed. The ratio measured in Oort cloud comets is slightly different from Earth's ocean water, which tells us something important about the origins of Earth's water. Most of it likely did not come from Oort cloud comets, but perhaps from a closer-in population of icy objects, the asteroid belt and the Jupiter family comets, that had a different D/H signature. This is an active area of research. The Oort cloud is also not perfectly stable. Every 10 or 20 million years, the solar system passes through a dense region of the galactic disk, a spiral arm, or a molecular cloud. And the increased stellar density and tidal forces on the Oort cloud produce what is called a comet shower, an elevated rate of long-period comets falling into the inner solar system over a period of millions of years. Some researchers have proposed that comet showers may correlate with mass extinction events on Earth, though this remains contested. If the correlation is real, then the Oort cloud, the outermost, most remote, most untouched part of the solar system, is periodically connected to events on Earth's surface in a direct, catastrophic way. The Oort cloud is silent, unseen, and in some ways the most significant structure in the solar system. It is the repository of the solar system's oldest material, the source of its most spectacular comets, and potentially the most distant actor in the drama of Earth's geological and biological history. No spacecraft has ever observed the Oort cloud directly. No mission is currently designed to do so. The distances are simply too great. Even with a gravity assist and the most optimistic propulsion scenario available in current technology, reaching the inner Oort cloud would take centuries. The Oort cloud is the solar system's largest structure, occupying a volume nearly halfway to the nearest star, and it is completely unknown except through inference and occasional visits from its most perturbed residents. This is humbling in a specific way. We know the Oort cloud exists. We know roughly how many objects it contains and what they are made of. We know it is the reservoir from which long-period comets originate. But we have never seen it, never visited it, never measured it directly. Everything we know about it was inferred from objects that fell out of it and came to us. Voyager 1 will pass through it, silent and blind, for tens of thousands of years. The Oort cloud will experience the passage of Voyager 1 in the same way it has experienced the passage of every other piece of matter that has crossed it, without awareness, without response. But the Oort cloud is waiting. It is the solar system's outer shore, and beyond it, at distances of a light year or more, is the beginning of the space between the stars. Not just the local interstellar medium that Voyager 1 has just entered, but the full, vast star-to-star gulf that separates the Sun from its neighbors. Chapter 12: The Anomaly That Wasn't, and What It Taught Us. Before we reach the conclusion, there is a story from Voyager's history that deserves a chapter of its own, because it illustrates something important about the relationship between precise measurement, theoretical prediction, and the kind of discovery that looks like a violation but turns out to be a clarification. In the 1990s, careful analysis of the trajectories of both Voyager spacecraft revealed a small but persistent anomaly. Both spacecraft were decelerating slightly faster than the standard model of gravity and solar radiation pressure predicted. The effect was tiny, an acceleration of about 8.74 times 10 to the power of minus 10 meters per second squared toward the Sun. But it was present in the data from Pioneer 10 and Pioneer 11 as well, and the consistency across 4 spacecraft made it very difficult to dismiss as a random error. This became known as the Pioneer anomaly. For a period of roughly 15 years, from the mid-1990s to the late 2000s, it was one of the most actively debated anomalies in fundamental physics. Some researchers proposed that it represented a genuine modification of gravity at large distances, a failure of Newton's inverse square law at solar system scales, or perhaps evidence for a fifth fundamental force. Others proposed mundane explanations: solar radiation pressure errors, gas leaks, or thermal radiation effects, but struggled to make the numbers work quantitatively. The Pioneer anomaly generated dozens of papers, several conferences, and a healthy amount of popular attention. It was exactly the kind of anomaly that physicists love: small enough to be easily dismissed, consistent enough across multiple independent datasets to be difficult to dismiss, and potentially significant enough, if real, to require revision of fundamental physics. The resolution came in 2012 when a team led by Slava Turishev at JPL published a comprehensive analysis of the thermal radiation forces on Pioneer 10 and Pioneer 11. The key insight was that the plutonium-powered RTGs on the Pioneer spacecraft radiated heat asymmetrically. More heat was radiated in some directions than others, because of the spacecraft's geometry and the arrangement of its components. the asymmetric thermal radiation produced a net force on the spacecraft, directed away from the Sun, which appeared as a deceleration toward the Sun when viewed from the solar reference frame. When this thermal force was modeled carefully, accounting for the spacecraft's geometry, the heat output of the RTGs, and how the thermal radiation was distributed, the anomaly disappeared. The Pioneer spacecraft were decelerating at exactly the rate that classical gravity and thermal pressure predicted. The Pioneer anomaly was not a violation of fundamental physics. It was a previously unmodeled force, the anisotropic thermal radiation from the RTGs that had been present all along but not accounted for. Why is this relevant to Voyager? Because the Voyager spacecraft have a different geometry from the Pioneer spacecraft, and the thermal radiation effects on Voyager are different in character. The Voyager RTGs are mounted on booms extending away from the spacecraft bus, specifically to reduce the thermal radiation effect on the main body. As a result, the Voyager data do not show the same Pioneer anomaly, confirming that the Pioneer effect was indeed thermal in origin. But the episode reveals something important about what Voyager's long baseline trajectory data can and cannot tell us. The precise tracking of Voyager 1's position and velocity over decades gives a measurement of the gravitational environment of the outer solar system and beyond with extraordinary precision. Any deviation from predicted trajectory can be interpreted as an unmodeled force, either a gravitational effect from an unknown massive object or a non-gravitational force on the spacecraft itself. This is currently being used in two ways. First, the trajectory data places tight constraints on the existence of proposed additional planets in the outer solar system. In particular, the hypothetical Planet 9, a proposed large planet at extreme distances from the Sun, suggested by clustering in the orbital elements of a group of trans-Neptunian objects. If Planet 9 exists at the masses and distances currently proposed, its gravitational influence on Voyager 1's trajectory would be detectable at some level. No anomaly consistent with Planet 9 has been found in the Voyager data, which places constraints on but does not rule out its existence. Second, the trajectory data acts as a check on our understanding of non-gravitational forces in the interstellar medium. As Voyager 1 moves through the interstellar medium, the very low but non-zero particle density exerts a drag force, extremely tiny, far below the current measurement threshold, but present in principle. In the future, as models of the interstellar medium are refined, comparing the predicted drag to any measured trajectory, anomaly could provide information about the medium's density and composition that complements the direct particle measurements. The Pioneer anomaly story is a microcosm of how science handles results that look like violations. The response was not to embrace a new physics immediately, nor to dismiss the data as error. It was to model more carefully, to account for all possible physical effects, and to let the data speak. The speaking took 15 years. The answer, when it came, was satisfying and instructive. The universe was not violating Newton at solar system scales. Physics was consistent, but the investigation revealed a previously unmodeled effect: thermal anisotropy. That is now a standard part of the analysis toolkit for spacecraft tracking at large distances. This is what careful science looks like. Not a revolution at every anomaly. Not dismissal at every puzzle. Engagement, analysis, modeling, and patience. Conclusion: the farthest thing we have ever made. Voyager 1 is right now somewhere beyond 165 astronomical units from the Sun. By the time you finish watching this video, it will be a few hundred kilometers further. By the time you sleep tonight, it will be about 1.5 million kilometers further. In a year, it will be 3.6 astronomical units further, about 540 million kilometers. It will never stop. There is nothing to stop it. It will coast through the interstellar medium, through the inner and outer Oort cloud, past the halfway point between the Sun and Alpha Centauri, for millions, billions of years, after every person who built it, launched it, tracked it, and understood it is gone. What has it found? It found that Jupiter's moon, Io, is the most volcanically active body in the solar system, driven not by its own radioactivity, but by the tidal energy of a nearby giant planet, a mechanism that has since been identified in exoplanetary systems far beyond our own. It found that Saturn's rings are not 2 or 3 broad bands, but thousands of intricate ringlets, braided by shepherd moons, sculpted by resonances, a level of structure that transformed our understanding of ring dynamics. It found that Titan's atmosphere is denser and chemically richer than Earth's, a finding that ultimately drove the Cassini-Huygens mission to land a probe on Titan's surface. It found the termination shock at roughly the predicted distance, confirming 30 years of theoretical prediction about where the solar wind runs out of supersonic energy. It found the heliosheath, filled with magnetic reconnection structures, the bubbles, that nobody had predicted and nobody fully understands even now. It found the stagnation region where the solar wind had completely run out of outward momentum and was simply sitting, compressed, waiting to be swept around the heliosphere's sides. It found the heliopause. It crossed it. On August 25th, 2012, at 121 astronomical units from the Sun, a spacecraft that had been launched in 1977 crossed from the solar domain into interstellar space for the first time in the history of human civilization. The crossing was confirmed not by the dramatic direct measurement scientists had hoped for, but by a solar storm event that had been generated by the Sun more than a year earlier, and had finally reached Voyager 1 across an incomprehensible distance, causing the local plasma to ring at a frequency that told scientists, unambiguously, that they were no longer listening to the Sun's plasma. It found the interstellar medium, its density, its magnetic field direction, its cosmic ray spectrum, its electron population, its plasma oscillation behavior. It found that the density increases gradually as Voyager moves deeper into the interstellar space, suggesting the spacecraft is moving from one interstellar cloud into another, a transition between volumes of gas in the galaxy that has never been observed from the inside before, because nothing has ever been inside one of them while crossing into the next. It found that the heliosphere is not a comet shape, but a croissant shape, and that the shape is determined by the interstellar magnetic field as much as by the solar wind. A finding that required a complete revision of the standard heliospheric model and is still being worked through in the theoretical literature. It found all of this with instruments that would be considered primitive by modern microelectronic standards, powered by a plutonium battery slowly winding down, sending data home on a signal that arrives at Earth with less power than a hummingbird's wing beat, But here is what I think matters most about Voyager, and it is not any specific finding. It is that something we made is out there. Not out there in the sense of the moon, where 12 people have walked and instruments have sat for 50 years. Not out there in the sense of Mars, where rovers have driven and the Perseverance helicopter has flown. Out there in interstellar space, beyond the sun's domain, in the space between the stars, which is where most of the volume of the galaxy is, which is where Voyager will spend essentially its entire future existence. We built a thing in 1977 with transistors and copper wire and a plutonium battery and 69 kilobytes of memory. We aimed it at Jupiter and Saturn and let the planets fling it outward on a trajectory that 45 years later carried it across a boundary that no human instrument had ever crossed. And it is still out there, still transmitting, still measuring, still telling us what the universe is actually like in a place that only mathematics and imagination had previously reached. There is no word for what this is except extraordinary. Not because Voyager is fast. It is not. A light beam crosses the distance between Voyager and Earth in 22 hours. Voyager would take 22 hours to travel a fraction of that distance. The galaxy is so vast that even Voyager's remarkable speed, sustained for millions of years, would barely scratch its diameter. We are not going to travel to the stars on spacecraft like Voyager. The physics does not permit it on human timescales. But Voyager is not trying to get anywhere. It is trying to tell us what it finds as it goes. It is the farthest finger we have ever extended into the universe, reaching into places we cannot go ourselves, returning data about a domain we understood only through theory until something actually went there. This is what space science is. Not conquest, not colonization, information. The universe is immeasurably vast, and we are very small, and Voyager is an instrument designed to compress some of that incomprehensible distance into a data stream readable by human minds. Voyager 1 will not make that final silence alone. Its twin, Voyager 2, crossed the heliopause in November 2018 at a distance of approximately 119 astronomical units, slightly closer to the Sun than Voyager 1's crossing point, consistent with the asymmetry of the heliosphere observed at the termination shock. The two crossings, separated by 6 years and a few astronomical units, are the only two direct measurements of the heliopause ever made. They crossed at different latitudes, different longitudes, different phases of the solar cycle. The comparison between them, the similarities and differences in the plasma density, the magnetic field direction, the cosmic ray flux at each crossing has already generated multiple papers and will continue to generate more as the data from both spacecraft in the interstellar medium accumulates. Voyager 2 still has its functioning plasma science experiment, the instrument that failed on Voyager 1 in 1980. This means Voyager 2, despite being somewhat less far from the Sun than Voyager 1, is providing direct plasma measurements of the interstellar medium that Voyager 1 cannot. The two spacecraft are complementary in precisely this way. Voyager 1 has gone further, but Voyager 2 has a complete instrument suite. Together, they provide two independent samples of the interstellar medium at different locations, measured with different but overlapping sets of instruments. Neither alone would tell the full story. Together, they are beginning to. In the late 2020s, when Voyager 1's power finally drops below the threshold required to operate its last science instruments, and the data stream goes quiet, there will be a silence in a JPL control room that has been monitoring this spacecraft since 1977. People who spent their entire careers on this mission, some of whom were children when it launched, will listen to the last signal, the last measurement, the last 22-hour delay before the data arrives. And then there will be nothing but the knowledge that the spacecraft is still moving, still coasting, still carrying its golden record and its plutonium battery casings and its 6 billion-year-old message into the quiet dark. In the long now, the scale on which this voyage takes place, the 50 years of Voyager's active science life are a single breath. What comes after is the vast, unobserved, unobservable remainder of its journey. Through the Oort cloud, into the deep interstellar medium, past star after star over timescales that make geological time look brief, carrying the evidence of a species that for a brief moment in cosmic history was curious enough to build something and throw it at the universe and keep listening until the power ran out. In the universe, Voyager is crossing right now. The stars are separated by distances so enormous that the entire volume of the inner solar system, everything from the Sun to Neptune's orbit, everything we have ever visited or observed up close, is geometrically negligible. Voyager 1, having crossed 165 astronomical units, has crossed a fraction of the distance to the nearest star that rounds to zero at most levels of precision. It is not, in the galaxy's accounting, very far from home. But it is further than anything we have ever made. And it keeps going. And as long as it keeps transmitting, we keep learning. That is the whole story. That is what Voyager is. A small machine made by curious animals on a pale blue dot, listening to the edge of everything with a transmitter smaller than most home appliances, sending back what it hears. Still listening, still out there,